Hello, all. This is Ricardo Castro at University of California, Davis. It's a great honor to be here for this plenary talk at the Advanced Ceramics and Applications 9. First of all, I'd like to thank the organizing committee for this invitation, particularly Professor Mitik. And I'd like to apologize not to be there in person as was my plan. As you know, the Delta variant of COVID has impacted the United States severely, and I have family and friends impacted by it, which is affecting our capability of going to Europe at this point. That said, I'll be happy to give the talk and to get the conversation about the topic. I'm going to leave my email, and please feel free to reach out, and so that we can really engage as much as possible. So I'm going to share my screen now and hopefully be able to see the material I have prepared for this talk. Okay. So one of the greatest things about that we use in ceramic design is basically the phase diagrams. Phase diagrams are critical for a design of applications, when you divide of a lifetime of materials, design of sintering, when you're looking for liquid phase states. These are really key aspects, and I can talk a lot about that, but most of you in the audience are aware of it, how true it is. And one thing that we actually miss it sometimes is that when you go to nanoscale, do those diagrams to work the same way? And what we learned today is basically they are not, and because there are interfacial terms in the energetics of these ceramics that will impact the stability of polymorphs. So, but before we go there, I'd like to share an important point for particularly designing for this meeting. As an editor-in-chief of the International Journal of Ceramic Engineering Science, which is sponsored by the American Ceramic Society, we have decided to create a special issue for this meeting. So this special issue will basically gather in different topics they are being given in this conference. And so I'd like to encourage each one of you to basically submit your paper to us. It's free of charge, and you're going to be actually promoting these within the American Ceramic Society marketing tools. So, you can rest assured that the paper will have great visibility. So Professor Mitik is an associate editor, and he'll be helping me out in these initiative. So I'll leave here my invitation for you to submit a paper, and you can follow this link here basically to the material, and you can learn more about it. So let's go back to nanomaterials and why nanomaterials are so different. One of the things that we have to understand is, like, when you're comparing a micromaterial with a nanomaterial, one of the classical obvious things is actually the number of interfaces that you have. Right, in this crystal here, you have just a few interfaces dividing these 9 cubicles here. Here you have like exponentially larger amount of interfaces. And what you understand is that if this is a magic cube, if you start moving this cube versus start moving this cube, you realize that there's a big difference in how you actually move this magic cube. So the same thing will be in the nanoscale. Because there are so much interface available, the mechanical properties of any nanomaterial will be intrinsically different than as compared to the micromaterials, just because I have more interfaces. The same thing is when you transform these cubes actually in powder, in fine powder. So instead of having grain boundaries, you actually have surfaces. And these surfaces will create also a different set of properties. Those surfaces now are active for gas sensing, for example, for catalysis. And this creates, again, a new universe of properties that you can only explore because you are at the nanoscale. So in our lab, basically what we do, we explore all these differences in the nanoscale and try to understand why they are different. So we look at a nanostability, surface chemistry, nanomechanics, radiation tolerance, sintering and grain growth, and activation field effects on interfaces, and trying to make sense of why is the nano so different. And what we've been learning is that everything is rooting back to the thermodynamics of the system. What do I mean, the thermodynamics of the system? So the energetics, the Gibbs free energy of these nanomaterials are intrinsically different. And they are so different because of the interfacial terms that even processes that typically you don't think about being related to thermodynamics, like nanomechanics, like the mechanical properties, become intrinsically dependent on those interfacial energies as well. Today, I'm not going to talk about nanomechanics. I'm going to talk mostly about the phase diagrams and trying to understand why phase diagrams are different than a nanoscale. And is there a way to design a new phase diagram for the nanoscale? And when I design them, how can I use them for engineering design? So let's start with this phase diagram. Well, I don't have to teach you the phase diagram of silica alumina. I'm pretty sure you're well versed on that. But basically, just a recap here, what a phase diagram is. So basically, we have a temperature and composition into two axes here. And basically, we can predict what is the phase of the material depending on temperature and composition. So this is a very classical one. So we have a liquid phase or static points, and then you know what the phase will be stable. Those are thermodynamically stable. Those are equilibrium states. So the assumption we make here, those are in equilibrium. And how to actually get to these phase diagrams? So if you go back to your thermodynamic books, you're going to say that, well, we have the Gibbs free energy of one phase versus the Gibbs free energy of the other phases. And the shape of the free energy curve versus composition varies with temperature, right? And depending on the temperature that you're actually going to have different stable phases. And this basically creates with all this information, you create your phase diagram. So the important thing here, the number that you're actually looking at is this so-called Gibbs free energy of the system, right? So, and this is technically just a bulk energy. In crystals, this means what is the crystalline phase, what is the energy of that particular phase in that crystallographic structure state. In the liquid, of course, this is one phase, in the liquid phase that also has this Gibbs free energy. But the fact is, if you started moving that to a nanoscale, this has to change. Why does it have to change? So now the Gibbs free energy of the system will no longer be just the bulk energy. We actually have to start inputting in the system also a surface term. Why is that? Well, if you do a very simple geometric calculation here of the fraction of volume of atoms within 1.5 nanometers of surfaces. So let's consider an atom here and a particle here, and the surface atoms, I would say that those are the atoms that belong to this 0.5 nanometer layer, core, a shell around those particles. If I do this calculation, I realize that the fraction of those atoms, when things go below 20 nanometer, increase almost like exponentially. So now, but these atoms here, they're certainly different than the one in the core. Why? First, because they don't have the same coordination, right? They're most an atom on the surface we have a half coordination in a perfect cut of a surface. But also, they have their bones that are unsatisfied, so you don't have right coordination. You have dangling bones, and this will bring excess energy to the system. So what you should expect from a system like that is that the energy of the system just go higher and higher and higher as the amount of atoms at the surface increase. This system here can actually be described by the gamma S, so like the surface energy of the system, times the surface area of the system. So the higher your surface area, the amount of surface per gram that you have, the higher will be the contribution of this term. And of course, this will start impacting the total energy, the total free energy of the system. And this will basically, at a certain point, affect your phase stability. But why would it affect the phase stability? The fact is, different crystals will have different bulk structures, right? That's what we saw in the previous diagram, showing that the free energy of two phases will be likely different. But also, it impacts the surfaces and there's surface energies. The surface energies of the system will also be equally different. And so what you realize is that in certain cases, you get into interesting situations where at the nanoscale, you can have crossover of energies. What do I mean? So let's take a very classical example of alpha lumina and gamma lumina. Well, alpha lumina is a corundum phase, hexagonal crystal, as you can see here, beautiful. And there is one transitional phase, it's called gamma lumina, which is actually a spinel phase, which is more like spinels are like cubic group. So they do have different energies in the book. So actually the energy difference between these two crystals here, just considering the bulk, is about 13.7 joules per mole, kilojoules per mole. And in this case, what it means is that this phase here, the alpha phase, is significantly more stable, more stable by 13.7 kilojoules per mole than the gamma lumina. So this is thermodynamically more stable. And if you go to the phase diagram, that's the phase you see that is actually stable, has the lowest possible energy. But interesting enough, when you're considering the surface energy of alpha and the surface energy of the gamma polymorph, what you realize is they have very different energies. And because the gamma phase is cubic, it's a more symmetric system. The surface energy of this material is much lower than the surface energy of the alpha crystal. And if this is the case, what does that matter? So it matters because if you start plotting a curve, which is surface area as a function of energy, what you see is that although when the surface area is zero, like in a bulk equilibrium crystal, the alpha polymorph is more stable than the gamma polymorph. This curve here will actually grow faster, have a higher slope because the surface energy is higher. So these grow super fast and the gamma phase grows slower. We're still going to grow because every surface will bring an excess of energy to the system in any case, but it grows slower with a lower slope. What will happen then is that eventually you're going to have a crossover. And if this energy difference is big enough, like it is in this case here, you're going to have a critical surface area about 115 meters square per gram here, where the gamma phase is actually more stable. Oh, what do you mean? You're saying that the polymorph stability change because at the nanoscale? So is this phase more stable? Well, the correct terminology would be metastable, right? This is a more metastable state, a metastable phase as compared to alpha lumina, because the surface is actually stabilizing under the same, as compared to the same condition, the same surface area of alpha. Oh, but the fact is, if my sample is in this condition, is at 200 meters square per gram, gamma lumina will always be gamma lumina and not going to transform into alpha. If I start coarsening this, putting heat on that, the gamma lumina grains are going to grow, and as they coarsen, they eventually will turn into alpha. So this alpha gamma transition is very well known, and it's one of the key examples where you have a surface stabilization, so of particular phase. And this gives you a glimpse of what is going to happen at the nanoscale to those phase diagrams that I talked about. But let's complicate things a little further, because one point is when I look at particles in the microscope, more often than not, more than just the surface, I'm also going to have these solid-solid interfaces, grain boundaries, right? And the question we have to you is basically, is the surface energy the same as of the grain boundary energy? And the answer is no. This energy will be different. And the fact is, now I actually have to recalculate what is the energy of my system, as I will not only have the surface contribution, but I should also have a grain boundary contribution if I want to make an actual description of my system. So this is the equation becoming a little bit more complicated, just with one more term here. Now, in addition to have surface area and surface energy, I have grain boundary area and grain boundary energy, as my system is composed by both surfaces and grain boundaries. This is truly a more realistic description of my particle. But the big question is that, does that make any difference in my phase stability? Well, the truth is it does. Let's take one example just to demonstrate how this is real. So let's take titanium dioxide. You probably read many papers about that, and understanding one of the polymorph is more photocatalytic than the other. So understanding this phase stability is really important at the nanoscale. And what you see is that first, similarly to alumina, there is a change in stability of the phase at the nanoscale. When your grain surface area is very much negligible, when it's close to zero, rutile is the phase where you expect to be more stable. That's a tetragonal phase. Based on the phase diagram, titania is stable in the rutile phase. And then it comes the bruchite and the anatase. But the fact is, as you go to small particles or high surface areas, right? The energy of rutile is higher than the energy of the anatase, for example, or even the bruchite. So what will happen is that as the grain size decreases, bruchite becomes more stable, and then anatase becomes more stable. That's why when you're actually synthesizing titania at very small particle size, you end up with anatase, not rutile, because it is technically more stable at surface areas around 100 meters square per gram. But as you coarsen that, you actually end up having a rutile effect as well, a rutile percentage in your system as well. But this is only considering surface, right? What about the grain boundary? So that's where we have this image here. So the surface energy of the anatase is lower than the surface energy of rutile. So we have a 0.67 as a function as compared to 2.06. And this is responsible for this crossover on this side of the diagram here. So we have surface area and energy, and you have this crossover, just like the one we saw in the previous slide. So there's a crossover right here of the stability. Rutile is stable here. As you go for small particles, anatase is stable here. So for big particles, small particles. But the fact now is that there is also a difference in grain boundary energy. So if I go to the extreme case where I only have dense samples, like with no surface, so like a fully dense material. So then I can write a graph that is basically grain boundary area as a function of energy as well. And so you see is that you have coarsened grains close to zero here, and you have fine grains, nanograins, titania, when you go to the high grain boundary areas. And because the grain boundary energies are different, you also have a crossover at certain point that will make a transition from the rutile stability range to the anatase stability range. But the key point is that because the energy differences are actually distinct, you would have these points of transaction, this crossover point at different areas. Oh, so does that mean that it really matters how sintered my materials are? Yes, it will matter how sintered they are and to determine what is the stable polymorph at that condition. So if I have free nanoparticles versus I have partially sintered nanoparticles, they will have different stability predictions. Oh, like for example, if I'm here at 4,000 here and my particles are free, I'm pretty much all titania. And even if I go to 3,000, they're all pretty much all titania anatases, right? They're all anatases, they're all blue at 3,000. But if I go for 3,000 here, it's already rutile. So 3,000 here is anatase, 3,000 here is rutile. So if I have some grain boundaries, I'm actually going to be transiting this change. You're going to have some interfaces that actually will allow the formation of rutile instead. So how much my particles are sintered will actually affect. And that's the key point of that. We actually did one experiment and looking into how the phase transition happens in rutile as a function of temperature. And one thing that we realize is that, so this is the percentage of rutile in my system versus temperature. And the percentage of rutile in my system just keeps going from 0, and eventually at 650, there's a jump in the formation of rutile. So start with anatase, becomes rutile. Interestingly, the grain size only evolves very slowly. But when you look at the density of material, there's a big jump in density when I shift in this position. Why is that happening? Well, now I'm actually activating sintering, and I have my early stage of sintering. What is an early stage of sintering? It's actually neck formation. As I have neck formation, it's grain boundary formation. So, in grain boundary formation benefits the formation, the formation of the rutile structure. Oh, this is quite an interesting proof. It's an indirect proof. They've already given an idea how complicated this problem can be. But if you're looking at complication, let's look a little further so you can see how complex the stability of nanoscale diagrams can be. So looking at this example of zirconia yttria. So as you know, there's great applications, ionic conductivity, toughness, transformation toughening mechanism in the system, and all strongly depends on the phase stability. When you have only zirconia, there's a classical transition from monoclinic to tetragonal all the way to cubic as a function of temperature. But as you add yttria, we know that the cubic polymorph becomes more stable with a bigger region of the stability of the tetragonal at even at lower temperatures as well. If I have nanoparticles, will these change? Well, the answer is yes, because the surface energy of these materials actually change as a function of composition as well. So this is surface energy of yttria, zirconia, nanoparticles as a function of yttrium. And what we see is that depending on your structural stability of monoclinic, tetragonal, cubic, or even in amorphous system, there is a change in surface energy. They have different energy in between those polymorphs, which is expected, as we know, but also within the tetragonal region, for example, here, you also have a change in surface energy with composition. Now we are adding one more variable to the system. It's not only phase and size. Now we have phase, size, and composition. And with changing composition, we're also affecting the surface energy. But you can remember, you can forget that yttria, the composition, is also affecting the bulk energy. So bulk energy gets affected, surface energy gets affected by size and composition. And if this is the case, we can actually write a new diagram, a phase stability diagram for yttria zirconia, as 0 is zirconium and oxide is zirconium dioxide, and up to 20% mole of yttria. And what you see is that there is a change in the phase stability region as a function of grain size because of all interdependence of the surface energy on composition and size. So this is the proposed new diagram for that. Very useful if you're interested in seeing like what's going to happen when you synthesize yttria zirconia. You realize that if you make small particles, you know, most likely you're always going to get to your cubic phase. But if you actually with particles around 100 nanometers, you're already supposed to be tetragonal. So very predictive. You know, we've done several experiments to confirm that, and really it's a very predictive system to help understand. We have done this for different systems as well, not only for zirconia yttria, but this is for zirconia scandia. We have this a little bit more complex phase diagram because scandia promotes monoclinic, tetragonal, cubic, the beta and the gamma phase as a much more complex phase diagram, but also all predicted by the group ring size and composition. We did the same thing for calcium zirconia. And actually, it's very similar to the yttria zirconia with a slightly difference on the sizes of stability, but quite similar to the yttria system expected. But even very different system here. This is a beryllium aluminate. So looking into the stability of my systems as a function of beryllium content, basically demonstrating that's also a big change in surface energies and bulk energies altogether. So, and honestly, we could go on for all the systems that we have, and it's just a matter of getting there and being able to deliver all this information. Because this is all true for all the systems, even for systems with high applicability, like for example, materials for batteries. Looking at a cathode structures, one of the materials that are candidates is lithium manganate, lithium manganate Mn2O4. This is one of the compositions, and it is very important to understand what is the phase stability of this material, particularly if you go to the nanoscale. Why would I want to go to the nanoscale in a battery? So think about it, like the lithiation dilithiation process is basically a process of stability of how much surface area I have in the system. So the more surface area I have, the more ionic exchange I can have. So lithium can go in and out quicker. So nanomaterials are known to be, a better option for batteries. The problem is that there's all this concern about phase stability, coarsening, cracking, and reactivity. Basically, what we're showing here is that one thing that we can help the community is by providing the phase stability diagram at the nanoscale. So when you're looking, for example, here, what happens with the lithium Mn2O4 is that it can actually collapse into Mn3O4 in the system. And from what we realize is similar to the system we just been discussing before, Mn3O4 is very more stable when they have large grains than small when they have large grains in the microscale. But because it has a higher surface energy than lithium manganese 2O4, there is actually a crossover at a certain point, also making it less stable, and you go to the nanomaterial. So this provides a better understanding of what is out there in terms of nanostability diagrams applications. So the big question in all of that is, you might be thinking is that, hey, where did I get all this data? Because different than what you think, that surface energies and grain boundary energies are numbers already standardized, and that you can go to the back of like journal physical chemistries or journal physical chemistry books and look in the back of it and say, hey, this is the data I want. You realize it's very scarce. There's not a lot of data on surface energy. So our group has dedicated a lot of energy into developing this calorimetric techniques to measure interface energies. So one of the techniques that we use is drop solution calorimetry. So when you do that, you basically dissolve a microsystem and dissolve a nanosystem, and then you calculate, when you actually estimate what is the difference of energy, and then you give me the excess energy of the nano world, right? Or also the other techniques is basically water absorption surface energy measurement. And this is a more complex and elaborated thermodynamic cycle, but you also can measure the surface energy of nanocrystal. And the other one that I'm going to be briefly talking is the DSC of sintering. So DSC stands for differential scanning calorimetry. And what we're doing, we're inducing sintering of your nanoparticles inside a calorimeter. And what it does, we actually measure the heat coming out of the system. And basically, when it's transforming from a nanoparticle at 850 in this case here, all the way to a large particle. Well, this is, we'll call it state 1, and we call this state 2. So we have a surface area here, we have a surface area here, we have a grain boundary area here, and a grain boundary area here. And basically, when you do this experiment, you're going to get a heat effect of sintering and compare state 1 and state 2. But then what you realize is that, I have 2 variables and 1 equation. So what we do, I run these experiments at different conditions and combinations to create a system of equations where you have 2 variables and just as many equations as variables. So that I can calculate what is surface energy and grain boundary energy. There's a lot of literature about that. I won't have time to detail that. But again, as I said, I'll be happy to discuss all these methods with whoever is interested in them. So as a conclusion, to be brief, so basically thermodynamics of interfaces are really critical when you're predicting nanoscale behavior. So I hope after this talk, you understand you're going to look different at your nanomaterials, in particular with regards to what is the phase that is stable. And start forgetting that phase diagrams, the traditional phase diagrams will predict your phase, because they won't. At the nanoscales, grain boundaries and surfaces will actually affect tremendously your system. And even get even more complicated when you have heterogeneous interfaces. Let's say you have materials that you have alumina zirconia interfaces. What are the energies of those? How much of those interfaces we have? Because if you have a lot, what we realize is that the whole phase stability will be affected by a more complex equation describing their Gibbs free energy. So we're hopeful, though, that our colorimetric techniques will help this process and really give more of this information to the engineers, so that at a certain point we'll be able to fully predict what's happening in the nano world. So I'd like to thank you again for listening. I'd like to thank the Army Research Office and the National Science Foundation for funding most of our work. And also I'd like to thank my group, who are actually the ones that go into the lab and do all the hard work. Thank you one more time. And if you have questions, here is my email, rhrcastro@ucdavis.edu. Please reach out, and I'll be happy to establish a fruitful conversation. And before I end, please make sure you submit your paper to our journal IGCS. I will be bugging with you with emails to make sure that we get your contribution. Thanks again for all, and I hope you enjoy your dinner that's coming after that, I understand. Thank you.